Good morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next part of Unit 3rd, and this is related to noise, the noise which will be going to affect the channel. So, the noise that we consider is Gaussian noise. Gaussian noise is statistical noise having a probability distribution function equal to that of the normal distribution, which is known as Gaussian distribution. So, basically why we consider only Gaussian noise, because its PDF is from minus infinity to infinity we are going to draw, it will be n naught by 2. So, that is a constant. So, that is the PDF of this particular random variable. When it will be extended from minus infinity to infinity, its amplitude will be n naught by 2. So, Gaussian noise is statistical noise having a probability distribution function equal to that of the normal distribution. The PDF of this noise is given by this formula. Here a random variable z is been considered, where z is represents the gray level, mu is the mean and sigma is the standard deviation. So, that is a very famous formula of the Gaussian distribution. So, this is 1 upon under root 2 pi sigma square e to the power minus z minus mu whole square upon 2 sigma square, where mu is the mean and sigma is the variance of this Gaussian noise, Gaussian function you can say. So, where it can happen? When we are talking about communication, then there the very simplest kind of model of a communication system is there is one transmitter, then there is one receiver, and in between this there will be a channel. Now, through this channel the signal will going to travel and it will going to reach the receiver. So, this is the transmitter and receiver concept, where the signal will going to travel from the channel. So, at this channel the noise will going to affect the quality of the signal. So, this is where the noise will going to affect this particular channel. So, what we consider in when we are analyzing any kind of communication system, we are considering the AWGN noise, that is additive wide Gaussian noise. So, why we consider additive wide Gaussian noise is that first advantage is it is additive in nature, it can be added to the signal whatever is being generated over here. So, it will be added over here. So, this is additive. Then this will be wide Gaussian noise, means it contains all the frequency components and it will be extended from minus infinity to infinity up to the amplitude will be n naught by 2. So, that is the case for additive wide Gaussian noise. So, now they can be affected by Gaussian noise coming from many natural sources, such as the thermal vibration of atoms in conductors from the earth and other kind of other warm objects, and from the celestial sources such as sun. So, these are the sources where this noise can affect the channel. Now, next is noise in digital image. So, when we are analyzing any image, so it will be affected if it is a real time image, or if it is generated from a system. If it is a medical image, means it is captured by X-ray machine, it is captured by MRI or CT scan. So, all these contain some kind of noise. There are different types of noises, like ultrasound image is affected with speckle noise, and there is salt and pepper noise is also there. So, you can see that when this is the original image, when this is affected with noise, so you can see a hazy effect of this particular image, from where you cannot figure out that what is this image is all about. You cannot figure out, let us take an example of a X-ray, and if doctor wants to analyze some disease and the image will looks like somewhat this. So, it needs some kind of image processing concept, where different types of filters can be used to reduce the effect of noise, and then the disease can be analyzed by the doctor. So, that is the case, that is the use of filters to reduce the effect of noise. So, it is also used in security. Sometimes Gaussian noise is deliberately added in the images to secure it from hackers. So, the example is cryptography. Now, what is cryptography? Cryptography with images, and I am going to explain the cryptography with the bits. Let us say I want to transmit 1011. So, this is only 4 bit of data. I am adding intentionally 15 bits of data. So, that is known as PN sequence, or we can say it is a kind of pseudo random noise. No, so this is generated by a noise generator that will going to generate any random number of bits which is having 15 bits. So, this 15 bits is modulo 2 added with the original 4 bits, and then we are having 19 bits of data. So, this 19 bits of data will travel over the channel, it will be received over here. Then again at the receiver side we require same 15 bits of this PN sequence, then it will be demodulated to 1011. Now, there is some drawback, there is some advantage of using this concept of ciphering, we can say, of encryption. What is the advantage is, this 15 bits of data is randomly generated. Every time you are using the noise generator, it will going to generate this random data. So, it is a kind of key only to open this data. The receiver should have these same bits. If this bit is changed, then it will not be demodulated to its original message. So, that is the main concept behind cryptography, that is deliberately added to the main data, so that it will be secured. The main aim is to secure these 4 bits of data. So, if third party or if someone wants to analyze what is the actual data, so whichever is having this key, which is PN sequence, can going to demodulate this 1011 of original data. So, that is the main concept behind cryptography. There are two types of keys that are used in cryptography, private key and public key. Private key is only been shared between the two end users, that is at the transmitter and the receiver side, whereas public key can be used by any of the users, but they have to have access over this particular PN sequence. Next is noise is wireless communication. The performance of the wireless communication system is highly determined by noise, particularly if the signals are in a fade, the signal to noise ratio can be low and burst of errors can occur. So, what is burst of error? Let us say when we are talking about digital communication, then bit error rate plays an important role, and when we are talking about continuous time signal, then signal to noise ratio plays the important role. So, what is bit error rate? Let us say I have transmitted 20 bits and 2 bits are somehow we could find out that 2 bits are corrupted. So, that means the bit error rate will be 2 divided by number of bits in the data. Let us say we have taken 20 bits. So, this is the bit error rate, whereas in case of signal to noise ratio we have to calculate the signal power to the noise power at the transmitter and at the receiver both side, that is signal to noise ratio at the input and signal to noise ratio at the output. Now, from that signal to noise ratio we can find out a parameter that is known as figure of merit, that will going to decide the noise performance of any kind of receiver. It can be a DSP-SC receiver, it can be SSP receiver. So, we have to consider a receiver model, and then at the starting of the receiver model and at the ending of the receiver model you have to calculate SNR. Then the ratio of this SNR will, from there we can find out this parameter, that is figure of merit. The inverse of figure of merit is a parameter that is known as noise figure. So, these two quantities are unitless quantities, and these are most important to calculate the performance of any kind of receiver. The wireless system, in particular cellular system with dense frequency reuse, are interface limited rather than the noise limited. Now, we talk about AKGEC. A basic and generally accepted model for thermal noise in communication channels is the set of assumptions that we are going to use. So, why we consider AKGEC? First one is noise is additive in nature, that is the received signal equals the transmit signal plus some noise, where the noise is statistically independent of the signal. The noise is white, that is power spectral density is flat. So, the autocorrelation of the noise is in the time domain is 0 for any non-zero time offset. Also the noise samples have a Gaussian distribution. So, that is the case why we consider this AWGN, because the analysis of this Gaussian noise or Gaussian distribution, what we say, is much more simpler as compared to the other types of noise. So, that is why from the mathematical point of view, from mathematical analysis point of view, we consider AWGN noise. Now, this is the Gaussian noise, can be represented by a distribution of fluctuations about the mean. So, this is, you can see that its value is maximum at mean and fluctuation is there around the mean. So, its formula will be for random variable x, it will be 1 upon sigma under root 2 pi e to the power minus x minus mu whole square by 2 sigma square, where mu is the mean and sigma is the variance of the particular signal that we are going to consider. The common characteristics of this AWGN is the Gaussian filter is a non-uniform low pass filter. Central pixels have a higher weighting than those on the periphery. Gaussian filters might not preserve image brightness. So, that is why these are the some of the common characteristics that we consider while designing any kind of Gaussian filter. Now, next is the bit error rate. Now, as I have discussed that in case of digital information, the bit error rate plays a very important role, where number of bits which is affected with noise is calculated, and then we consider a parameter, that is bit error rate. So, it is the number of bit errors per unit time. The bit error ratio is the number of bit errors divided by the total number of transferred bits during a studied time interval. So, bit error rate is a unitless performance measure, often expressed as a percentage. So, it will be expressed as a percentage also. So, how many bits are affected with noise? Next is the bit error probability, PE is the expectation value of the bit error ratio. The bit error ratio can be considered as an approximate estimate of the bit error probability. This estimate is accurate for a long time interval and a high number of bit errors. So, that is the concept of bit error rate. Now, this is a very nice diagram which will going to explain that what is bit error rate. Let us say there is a transmitter, this is an interfacing unit, and another, this will be the end unit. This is the clock signal, means for a particular time slot. Let us say for 5 seconds we are for first 5 seconds we are seeing one kind of signal, and then during this the data will be considered, and then at the receiver side we will going to analyze the data, and we can compare the what has been transmitted and what has been received, and we can consider that what are the number of bits that are in error. So, bit error rate is equals to total number of error bits divided by total number of bits. So, let us say there are 1 bit and total number of bits which are transmitted is 8. So, 1 upon 8 is the bit error rate that we have calculated, number of bits which are in error divided by number of total number of bits. So, 8 bits we have transmitted and 1 is having an error. So, that is the case of bit error rate. Now, bit error rate in telecom. In telecommunication transmission, the bit error rate is the percentage of bits that have error related to the total number of bits received in the transmission, usually expressed as 10 to a negative power. For example, a transmission might have a bit error rate of 10 to the minus 6, meaning that 1 out of this number of bits transmitted, 1 bit was in error. So, means 10 to the power minus 6, which means 1 out of 10 to the power 6 number of bits is having an error. So, this is how we can find out the bit error rate in the telecom. So, the bit error rate is an indication of how often a packeter or other data unit has to be retransmitted, means whenever there is error occurs at the receiver side, then the data packet has to be retransmitted again, means, and if there is a negative acknowledgement is being sent, let us say this is a transmitter, this is a receiver, then packets of information is being transmitted, let us say this packet is transmitted. Now, the transmitter has to listen for an acknowledgement. Now, acknowledgement can be ACK, acknowledgement can be positive, it can be negative also. If it is a positive acknowledgement, which means that the data which is received is having positive is received without any error, then positive acknowledgement will be received, or if somehow it will be lost, or if there is any problem, then NAK, negative acknowledgement, will be received. If this negative acknowledgement is received, then the data has to be retransmitted again. So, for that retransmission request will be received at the transmitter side. So, that is the case of negative acknowledgement. So, this is a two-way kind of communication, means full duplex. So, too high a bit error rate may indicate that a slower data rate would actually improve overall transmission time for a given amount of transmitted data, since the bit error rate might be reduced, lowering the number of packets that had to be resent because of an error. Now, next is the white noise. So, what is white noise actually? The white noise is another name for the thermal noise or the Gaussian noise. Basically, there are two types of noises that exist, that is internal noise and external noise. Internal noise means whatever noise is there is internal to the system. It is going to affect the system at the component level, means if there is any problem, noise generated due to resistance, capacitance or inductance of a circuit, then that is known as internal noise. So, there are 5 types of internal noise. First one is short noise, next one is partition noise, then this will be flicker noise. Flicker noise is also known as low frequency noise because its PDF is inversely proportional to the frequency. So, that is known as flicker noise. Another one is transit time noise. So, that is known as high frequency noise. Last one is thermal noise. Now, this thermal noise, it is also known as white noise, it is also known as Gaussian noise. Now, why this is known as thermal or white noise? Because this property concerns the temporal variation in the individual noise samples that will affect the signal. White means it refers to the frequency decomposition of the sequence of noise samples and essentially says that the noise signal contains the components of equal expected power at all the frequencies, means it will consist of all the frequency components that we require. So, that is the case of thermal noise. The main formula of this thermal noise voltage will be Vn is equals to under root 4 kTBR, where B is the bandwidth of the system, R is the resistance over which we have to calculate its value, T is the room temperature, K is Boltzmann constant. Boltzmann constant value is 1.38 into 10 to the power minus 23 joule per degree Kelvin. So, that is the value of Boltzmann constant. So, we can calculate the thermal noise voltage using this particular formula. Also, we can calculate the noise power, which will be equals to KTB, where K is the proportionality constant, again the Boltzmann constant. So, this is all about internal noise. Next one is the external noise. External noise is related to when the noise is due to sun, it is solar noise. When it is due to stars, it is known as cosmic noise. It will be industrial noise, it will be atmospheric noise. So, these are kind of external noise which is external to the system. So, this is all about white noise, or this is all about different types of noises that will going to affect the quality of the signal at the channel. Thank you.